Norway. And I started in Norway in an institute called the Hos Colin E. Olson, and it's a university college. And it was in fact a research teaching-based institute. And now we become part from Norwegian University of Science and Technology in 2016. And since that time they try to push this small institute into more research. So we try to be more active in research. So I did a PhD in artificial intelligence in South Korea in 2011. And in 2012 I did another PhD in field robotics at Aarhus University in Denmark. And I was working in robots in agriculture. So I was developing these pest planning and field coverage algorithms for harvesting, seeding, and so on. And I got a postdoc in area of social robots also at Aalborg University. And now I'm working also to some degree with social robots. And it's important for Norway because they have lots of, they have, a number of larger sector of, all the citizens or all the people, and they try to maintain the same level as it is today, for example, in the future, and they want to use technology to keep this level at the same level today, because educating people to work in area of social or social services and taking care of all the people, it takes lots of money and resources, and also they need people to work, so they need to use robotics in this area to assist people who are working in those elderly care facilities to keep the same level as it is today, for example. Yeah, so robots not only in factories, but should, in the future it will be maybe in classrooms and in nursing homes and in hospitals. Yes. So I'm working also as I'm leading a small master program in simulation and visualization, and we have around 25 students, and we'll try to attract more. So I will talk also about this master program today, and I'm leading this research and innovation in my institute. We are very, very small one. We are in total 30 persons working, including people for administrative stuff and so on. So effectively, maybe we are like 10 persons who are teaching and doing research in the department. So this is the research activities at my department. In 2016 we have no research in fact. So we started by creating new research groups, one in digital, called digital transformation, and one called cyber physical system. In digital transformation, we are working in social robots. We have a PhD and a postdoc working in this area. We have simulation and visualization. We have a theater called the simulation and visualization theater, and we will try to visualize systems, visualize data in this one. And it's connected with the master program in simulation and visualization. We have something called the TAFT lab, and this TAFT lab, it's a lab which is funded by a bank, and they try to use artificial intelligence and machine learning in the area of finance. In cyber physical systems, they have this marine technology. So they try to build autonomous systems. We have larger groups working in different areas at NTNU in this area, but they just started very small group with some PhDs and some postdocs. In medical technology also we have some master thesis, master students, bachelor students, and one PhD, and they are working in medical image segmentation. For example, they take a scan of a knee and they try to build a 3D model for it, so they can train doctors and they can make diagnosis early. So we have some research areas at NTNU, and we are working on some of those research areas. We cannot cover all of them. For example, we are working in autonomous systems, we are working in artificial intelligence, data science, digital enterprise and business, and the digital twins. So we try to work in some of the most important areas for the faculty in order to be able to get money and fund for. So the study program, it's 120 study points, and it's 2 years the study program. And it's about simulation and visualization. So the courses are divided into some of them for simulation and some of them for visualization. We have also machine learning, we have swarm intelligence, we have virtual world, and we have something called a specialization project, and it's 15 study points. And the students here, they start working early in the second year in a task in collaboration with industry, for example. And they can use this one as an introduction to the master thesis. So you can start here and continue working into their master thesis. And in this case, we can have them working for 1 year on one task to get more mature results. Because before, it was a very short period, and sometimes the people cannot submit their thesis on time, and we need to make an extension, give them extensions, for example. and sometimes they can do some results, but they don't have time to write a paper, for example. So now, using this approach, we can have more time. They can have more time to start early, working in the thesis, and also maybe submitting, writing some articles at the end of the master thesis. We have something called experts in teamwork, and this experts in teamwork, it's not a course, it's like a group work, and the idea behind it is to teach students more transferable skills, how to deal with a group, a project, leading a project, presentation skills, writing a report, and so on. So in experts in teamwork, in fact, it's a team which consists of one from different study program, and they are working together. For example, we are in ICT, so they have one from ICT, other people from international business, for example, one from marine operations, for example, and so on. And they work together and they try to solve a problem and how to deal with each other. So the idea is to teach them how to work together, different team, interdisciplinary, and provide solutions. The master program, in fact, it's about simulation, visualization, artificial intelligence, because if we need to build a model, we need to maybe use data mining techniques, AI techniques, in order to update model parameters to reflect reality. We use visualization also to visualize data generated from a model, for example. And in the middle, we work with digital twin, and we will hire a new professor in digital twin, so we will get it online very soon. So hopefully we can get a new professor in digital twin maybe after summer.
And double the...
Yeah.
Can double the people with twins.
Yes, good idea. Yes. So in social robots, I started working in social robots also in 2016. So we built this small social robots lab because we are just 2-3 persons, and we have some people working with us from health science. They provide us with inputs, and when we build some functions, we try to test it in a nursing home with old people. So we try to see how it will impact people in nursing homes. So we work with the commune, the municipality, the Department of Health Service, it's a health science department. Also in the hospitals and this Haram Omsorg Center, it's a nursing home where old people live. When they reach a level, when they cannot live independent, they usually move to this Omsorg Center to take, so someone else can take care of them. And they want, in fact, they have a problem because they don't have enough people to work in those institutes. And they need to use technology, IoT, for example, technologies and robots to support the people who are working in those places, so they can maintain the quality at the same level, for example, because it's expected that the quality will degrade if they didn't use technology for helping them. And working in social robots, in fact, it's exciting because it's a problem. Some people support it, some people don't support it. So when we do an experiment there, we got lots of support from some, and in fact we used it in some places. We started using it in a school where we used this now robot, for example, to assist. We used it in something called Newton room, and this Newton room, it's a lab, and this lab they just try to attract the kids to study math and science. So we use this robot in this Newton rooms to help the room teacher to present modules and experimental stuff which he would do, because in his daily life there are things which are just repeated every day. So we try to take those stuff which can be used by a robot, and the robot, in fact, he just make presentations, so he present it to the students. So in fact, we build a simple software, so the teacher can just upload any PowerPoint to the robot, and the robot will present it, and they will just present and read it, in fact. And just each time he will just try to move like a human, so we'll just try to mimic a human person in presenting stuff. And it was very nice, in fact. And also, in fact, we used it in schools and in this nursing homes, even in opening of some departments. We try to use those robots and make a show with the person who was singing. So it was very nice, in fact. Some people are supporting it, some people are not supporting it. It's just from some newspapers. And we used it in this Omsorg Center or nursing home, and it was very useful. In fact, the people like it very much. All the people like it, but also they are worried about this idea of warm hand. So this person, for example, he said, "Najtak tel robotar I elder Omsorg Center," for example. So we said, no, we don't want those robots in the nursing homes because they are worried. They said, when we are in this level or this stage, who will take care of us? We need human people to take care of us. But it's a problem. I mean, it's the same. People also resist it because of jobs. For example, people feel that it will take jobs from people. So we try to inform them. It's just to assist you in your workspace to have better life. Quality of life in your working atmosphere. But it will not take jobs from any other people. And of course, at the same time, it creates another jobs. So if we need to build those systems, programming them, of course we need people to do this. So in fact, it creates jobs. So,
do you, because you showed example of just example, but did you or other researchers conducted like scientific experiments to, I don't know if how you could devise a metric or something to evaluate if this is really good or not?
Yeah. In fact, we did very small because we just started. Soon. We did an experiment in the Omsorg Center, and we built a robot to communicate with the people in Omsorg Center, and perform as assistant personal trainer. So we assume that people in the nursing homes they are not able. In fact, they have physical problems, and they are sitting on the chairs. So we developed some simple exercise. So the robot can encourage them to just exercise from time to time while they are sitting on the chairs. So in fact, it's a simple dialogue system, and the robot just talk to the people and give them say some jokes or some stories to warm up and to make it more nice atmosphere. And after that, he will just encourage them to practice exercise. So they are sitting on the chair, and the robot start moving and instructing them how to move like this. I have a video, but maybe it's not here. So they start to exercise, for example, and chat, and maybe an old lady can ask the robot to tell her a joke, for example. You can just say a joke. We have some jokes. And also it can get access to some news, maybe about weather forecast, the day of today, for example. So we have, and they evaluated it because we have very small, the experiment, we did the experiment in this small Omsorg Center or nursing home with maybe like 7 or 8 older persons. So we have people from health science, they made an observational study, and they published it, and they said it has impact. In fact, on it's just make it's more exciting for the old people who are living in the nursing home, but it's observational study. It's not statistical significant study. It's just observation.
There is no, for instance, comparison between the results with a real person and compared to the result with the robot to say, yes, this has a real impact and this is different, or this should be combined with real people. And
in fact, they published one paper, and they just did a questionnaire with the older people and interviewed them after a meeting with the robot several times, and they said they like it and they enjoy it, but they want it to be more smart. Because in the communication, after 10-15 minutes, they discover that it's like hard-coded dialogue system. So they discover that it's not smart enough, and they want it to be smarter, but it's just by interview. So just interview with them and ask them, but we don't know if it is really good for practice or not, if it will encourage them. Maybe this is a wow impact. People maybe will like it because it's the first time to see a robot, for example. So in fact, we need to have more experimental studies in order to prove or disprove if it is useful or not. Yeah. But in this, I mean, the idea is to build long-term relationship with the patient. So we started by building user profiling. So the robot just will take the image of the person, and it will try to recognize him, and it will run a simple dialogue system with the person for the first time, and store its basic information, name, and stuff like this. So next time it will just use his first name to talk with him, for example. In this case, it will give a nice feeling to the person, and after that, it will just try to make those simple exercises with the people in the dining room. So, but we have a PhD who will start maybe after Christmas, and we have a plan for him to make more experimental stuff. Yeah. But now at the moment, in fact, we just did this work with bachelor groups and the master study thesis. So we have one bachelor thesis or 2 bachelor theses and 1 master thesis for doing this. But we don't have people really who are working in it right now. We are waiting for one PhD student to start after Christmas. Yeah. So I will talk about my work in my PhD. I was working in this best planning for robots in agriculture. So I will talk about, but in fact I will talk about a paper which I presented in 2016, and it's about best planning for robots for land mining, detection and clearance, which is important area. So how to speed, the idea is how to speed up land mining or land mine clearance and make it safer. So we need to use robots instead of using people searching for land mines and deal with it. So in fact, I have been working in those projects before. So I have been working in road planning and field coverage algorithms for autonomous vehicles. And it's simple. We have four-wheel robot, for example, and this four-wheel robot has an implementation. Maybe this implementation it's maybe for seeding, for harvesting or whatever. And we need to cover a field in an optimized way. So so it could be robot like this one. It's a Horty boat at Aarhus University. I'll start with it. And it could be, for example, this Habco autonomous tractor in University of Copenhagen. This one also, it's a Rock at Aalborg University. We have been working with it. And the idea from this one also is to have a best planning, so the robot can cover some area. In fact, in this project, we have a helicopter, and this one, it take aerial images of the field, and they describe it identify areas which has wheat, and we send those locations to the robot, and the robot can go into those spots and spray it. So they try to minimize amount of sprayer, which herbicides, for example, to just have clean environment. So, and this one, it's line marking robot, and also it was a paper in my PhD, in fact, because in football fields, some people, they draw those white lines, right? And it's expensive. It costs, I guess, 1,000 euro on average for each football yard. So the idea also is to build a robot which can do it automatically, for example. And of course, it should be more accurate than human. So, in agriculture, in fact, we have a field, and we need to maybe harvest or seeding the field, and we have a four-wheel robot. So in fact, we just need to identify a point, entrance point to the field, and we can have some the outer bounding box of the field, or the we need to get field boundaries, and after that we need maybe to get the driving angle and operating widths of the four-wheel robots or the tractors, for example. And we can use some optimization algorithm to optimize the driving angle. Because if I have a field, and usually drivers, they select this longest side. They prefer to drive parallel to this one, because this is the long side of the field. And in this way, in fact, when they drive along this one, they try to minimize number of turnings at the end. Because the number of turning at the end, it's not efficient to drive, it's a non-efficient driving. So some drivers, they can just select this one, for example. Maybe some drivers, they will select something else. And in fact, it's habits of tractor drivers. They just repeat it year after year. Sometimes it's okay, sometimes it's not the optimum choice. So in fact, the idea is to generate this one automatically and try to use an optimization algorithm to find the best trajectory which we can use to cover the whole field. So in fact, we try to generate a less number of tracks, because when we generate a less number of tracks, we will have less inefficient driving at the end. Because when I finish a track and I try to turn and to go to the second track, this part is inefficient. So if we try to minimize this one, we can get better driving in the field. And at the same time also, soil compaction, because when you drive a lot in this area here, we call it the headland, for example. When we drive a lot here, this area will be compacted, and it will have some negative impact on the production. So people also, we need to try to minimize the soil impact. So we have the soil impact which we need to minimize. We need to minimize also amount of driving in the field by selecting the best driving direction. And also, when I finish a track and go to the second track, maybe if the working width is smaller, it will be very hard to just go directly to the second track using this pi turning time, because it will be more complex. So in fact, we can, maybe we need to use the fishtail one, with fishtail which is more complex. So the fishtail, if I will go out from here, for example, so in this case I need to go to this one, so I need to go in this direction, or go in this direction, back and forward, so we can go into the second So in this case, we need to reverse the direction and it will take time. So in fact, if we need to minimize the amount of driving, soil compaction, we need to minimize, we need to sort the tracks in a way to use a simple turning type, not the complex ones. Because if I will finish this track and I need to go to the second track, I can just follow it in this way, but in this case I need to use very complex turning type in order to enter to each track. So, but if I can escape one track, for example, or if I can use an optimization algorithm to sort the tracks, we can get better solution. So in fact here we use the field boundaries as an input to the program, and the driving direction. Maybe this driving direction we can use an optimization algorithm to find it, and also the order or the sequence of tracks. So we can optimize time, maybe amount of driving, and so on. So in fact, I did that for different types of fields and agriculture, and I did that in two-dimensional space, and also I did that for fields which are represented in 3D. Because in some fields are flat, which is easy task, but some fields also sometimes it's not flat, and it's hard and it's challenging for the robot to drive on those fields, especially when it's rainy, for example, slippery. So it will be very complex. So also we can optimize this field, which will be more challenging and more efficient. So we can just simplify fields, and we can use two-dimensional. We can represent the field in two-dimensional space, or we can represent the field in 3D, and we can use optimization algorithms for finding the best driving direction and the sequence of tracks. In the optimization, we can use single objective optimization, so we can just focus on, for example, single variable, single objective function, or we can use multi-objective optimization. And in multi-objective optimization, we have two objectives or three objectives which we need to minimize at the same time. So there will be some trade-off. For example, it could be the time, for example, and soil compaction. So which one is? So we can solve this problem as a single objective optimization problem, and also we can solve it as a multi-objective optimization problem. So this one, it's one example. It's a Robocone. Okay, so I have a video here, but maybe it's. I guess it's. So in fact, to use this robot, we need to use RTK GPS in the field to have better accuracy. So in fact, usually when we go for testing it, we use RTK GPS to have better accuracy. And I use the field outer boundaries for generating those tracks, use an optimization algorithm to optimize the driving direction and the sequence of tracks. And after that, we can just test it in the field. Yes, so it's just... So the second application also, which I mean, there is one company now working on this application. It's in line marking illustrations in football stadiums, and it's the same in fact. So instead of harvesting, we can just change the implement by using a plotter, for example. So in this case, instead of just driving and maybe cutting the grass or harvesting or spraying, we can just try to draw those lines in the field. So it's the same. I have also the outer boundaries of the field for football stadium, for example, and I just generate all those points and connect those points using doping curve. So we have this doping curve, so we can just connect it in a nice way and a smooth way, and we have the implement, and the implement it will be up and down each time for plotting the football those lines. So it's a nice application, and it's very useful because. So I can just show you this.
You could do the surfacing of the ice also for hockey playing.
What?
Surfacing the ice for hockey playing?
Yeah.
You could do.
Cleaning the ice?
You do the surfacing, you know? You pass on the ice to make the surface more flatter.
Yeah.
You could also find.
In fact, in this application.
In Norway, it could get.
Yeah. So now it's just a simulation. So in fact, I generate the point. I need a point, in fact, from football stadiums because it's a rectangle. So in fact, we just need only one point. So I start with a point and I generate all those points. and I generate all points and the curves in the football stadium, connect those trajectories with doping curve to be more smooth for the robot, and just send the trajectory to the robot, and the robot will just follow it with very high accuracy. So if we have RTK GPS in the field, the accuracy will be really very, very high. And in fact, I tested it with many football stadiums according to FIFA standard, and I found that some famous football stadiums, they are not very accurate as we imagine. Because they just, someone he do it, so sometimes it's not really a rectangle, which means maybe the game is not fair game, or but using it with the robots will be really very accurate. Yeah. And of course we can use it in golf, different types of games, cutting the grass in the football stadium also, and stripping it, correct? Because I can cut the grass in the field and stripping it in different directions. So we can do multitasking stuff in the football stadium. And it's useful because the average cost, in fact, today it's 1,000 euro, I guess, for each football stadium if you want to maintain it, because you need to do it and you need to repeat it maybe several times. So it costs a lot. And the robot itself, it's simple and it's cheap. And using this approach, you can just do it anytime. People will have better life. You can just do it before playing, for example, and during night time or whatever. But the problem is the RTK GPS, which we need to have maybe in a football stadium all time, or we need to install it when we need to do it. So in fact, a company from Denmark, they used my code, and also now they have built this robot. So it works very well, in fact. And they have two versions. One version now it's just for those time marking illustrations, and another one for cutting the grass. So we can cut the grass also from those football stadiums, stripping the grass to have different colors, because it will reflect the light in different directions. So we can have different to look more beautiful, and we can have all tasks because it's one robot with different implementation. So we can have only one four-wheel robots. One time with plotting, just it changes the implementation. One time for plotting, one time for cutting the grass and stripping. So it could be one machine for doing different things at the same time. So in fact, it works very nice, and as you can see, it looks very accurate. I don't know, maybe you cannot see it clearly, but yes. So in fact, we have one segment, and if I want to make this 90-degree angle, for example, I use the wind curve to change from one direction to the other direction, and it's very simple, and it generates the trajectory, and you can also simulate it. So in fact, I can store the trajectory as an XML file, for example, and display it in Google Maps. So this is how I make comparisons. So I can just get a point from any football stadium, and I can generate the trajectory for any football stadium, and upload the XML file again to Google Maps and display it. So you can just make comparison between reality and the one which is generated for the robot.
Maybe I have a question.
Yeah.
Okay, planning is important in this scenario, but here I believe that localization is also really important.
Very important.
Otherwise your planning
Yes.
would not be useful in the end. So what kind of device do you use for the positioning? It's a GPS or?
RGPS, RTK GPS.
Oh, okay, yeah.
Yeah, because the accuracy will be very high. Otherwise, of course, it will be impossible to do.
Yeah.
So they implement RTK GPS, before doing it. But I just need to get one point from the football stadium, generate the trajectory, and they need to install the RTK GPS and just run the robot. So for demining or mine clearing, it's also process of detecting and removing this landmine from an area. I'm from Egypt, and we have large areas with those landmines from World War II, and it's really a problem. It costs a lot, and also it has very, very severe impact, in fact, on people who are working on it. So, and it's a robot with an implement. In agriculture, we have a seeder, for example, a sprayer or whatever. But in landmine, we have this metal detector and products which remove those. So we need to detect the landmines we need to allocate it, and after that we need to deal with it. And it's much safe to work with robots instead of working with humans, because they have some statistics that for each 5,000 landmines, one person is killed, in fact, and it costs a lot. Because also people who are working in this area, maybe they start early morning with full mind and mentality are fine, but maybe by the end of the day they will just become fatigued and not accurate enough. So they will make lots of mistakes, and those mistakes it could impact them or impact other people, because they can just skip some areas, for example, or whatever. But if we can have a field, and if we can cover this field with high accuracy, it will be much safer, in fact, to work with robots instead of working with humans. So it's a very, very important area. So in fact, the objective here is to so the objective here is to replace human miners with fully autonomous robots system able to work around the clock regardless of working conditions and with high accuracy. This is very important for us. And it's the same also. I have a field, so I have 4 points, so I can just have outer boundaries of any field. You can just get locations from Google Maps or whatever. We have this outer field boundary, and we just need to generate a trajectory which can help the robot to cover the whole area. And it's the same, we can use optimization. It's the same, exactly as the same for in agriculture, but when we detect a landmine, we need to mark it. So we need to mark this location that we have a landmine in that location, for example. And maybe the robot should have a tool to deal with the landmine. So in fact, we use the minimum turning radius of the vehicle or the robot, because we need this minimum turning radius to generate how can I connect different tracks using doping curve, for example, and also the operating width of the vehicle or the robot itself, because this operating width, it will be the operating width of the track. So in fact, I'm using this, I just generate tracks parallel to each others with operating width distance from each 2 tracks. And topographical constraint of the landmine field, it could be in 3D, it could be in 2D, it will be okay. So the system requirement also, we need to have RTK GPS, and we need to have a robot with landmine detectors and the sensors, and we need to be able to deal with the landmines directly. So when we discover a landmine, we need to have an implement to deal with it, for example. So the vehicle will move in tracks, it will detect the landmines, and it will deal with it. At the end of the track, it will turn to enter a new track using Dobbin's curve or any types of curves. The order of tracks, the turning time, and the driving angle can be also optimized. So it's the same. You can use multi-objective or single-objective optimization problem for to sort the tracks in a way to have a simpler turning time from one track to another track. The driving angle, we can optimize it, because when we optimize for the driving angle, we will get a less number of tracks to cover the same field. So I can cover a field with 10 tracks, and I can cover it also with 20 tracks. Maybe if it is 10 tracks, maybe we will finish it in 2 hours. If it is 20 tracks, it will take maybe 4 or 5 hours. So if we need to optimize the operating time, for example, fuel cost and so on, we need to optimize for the driving angle. So we need to find the best driving angle in the field, which will generate less number of tracks to cover the same field area. And also we need to sort the tracks in a way to generate a simpler turning type between different tracks. Headland bases should be also cleaned first for safe turning. So before scanning a field, we need to clean the headland passes, because maybe it has a landmine and it will be a problem. So first we need to, so the order, we need to start with headland passes first, clean it, and after that we will scan the whole field track by track. In agriculture, for example, it's the same. So if you need, in fact, to harvest, we need to harvest the headland first, and after that we will go into the tracks inside the field. In seeding, if we are doing in seeding, for example, we need to start with the field, and after that we need to cover the headland passes. So this is the order. So it's the same also. The input to the maybe the algorithm or it's the field boundaries, number of headland passes, operating widths, minimum turning radius, and the robot initial position, for example, or the entrance point to the field itself. And we will generate those headland passes, and after that we will generate field tracks, and we can use some optimization algorithm to find the optimum driving angle and the sort. We need to sort also the tracks in the best way. and we will generate the trajectory, and I will convert U to M into degrees, for example, and put it in XML file, and we can visualize it in Google Maps if we want. I use the doping bases to connect. The doping bases, it's just we use it to connect different tracks, and it's one of different algorithms, in fact, and they call it the track transition curves, for example. So we use this one in order to connect the tracks. There are many different types. For example, RSR, it means we will go right, straight, right. This one, it's right, straight, left, left, straight, right, left, straight, right. So it's according to the direction and the orientations of tracks. We can select the best configuration for dope and pass. So for example, this one, it's RSL, which means, for example, maybe I'm coming from that direction, and I will go right, straight, and after that left. So it's the way how can we connect the tracks using doping curve. So for example, this one, it's LRL, which means we need to go left. We need to go, it's left, right, and after that left. So we use this one for connecting those tracks. I have an example. I have a field. It's in Egypt. It's in the north coast of Egypt, and it's this area. In fact, it's a very famous area because it was in World War II. They have lots of fighting here between German and British. It's called Al-Alamein field, and it has huge area. It's unused, in fact. It's. I mean, if I can show you in this area in Google Maps, just maybe few kilometers in this direction, you will see nice water, and the north coast is very, very beautiful area. Nice water and beaches, but it's not used. No one can use those areas because all those areas are covered with landmines, and because of shifting wind, sand, locations are different. No one can know where is it located now. You don't know also if it is deep or it's.
And because they have moved, it's even more dangerous.
Yes, so it's very, very dangerous. So sometimes local people are living in those areas. They just go because they are just living there for many times. But I mean, lots of people are living there. It's without legs, and they kill people and they kill animals. Lots of people, disabled people living in those areas because sometimes they are not careful, in fact, and just go driving and. So it's a problem. They kill many people, and many people disabled because of those landmines. So it's a really big problem here. If I have the map, I will show you very, very beautiful area. In fact, if you go just north here, very, very beautiful beaches, but it's not used. It's not
accessible.
Not accessible because of this problem. So it's a huge problem. So I used this one just an experimental field, and I used the coordinates. I just selected a bounding box of this area. So I just have maybe 4 or 5 coordinates of the area, and I use the two headland bases, for example, 20 meters operating width, 65 driving angle with eastern directions. 42 tracks are generated to cover the field body after headland area. So I can just generate a trajectory, and also I didn't optimize. In fact, I just selected the driving angle by myself. But if you want to optimize it, if you can choose complex shape, for example, so it's much better to use an optimization algorithm to select the best driving direction in this field, and also to use the optimization algorithm to order the tracks. So which order, what is the best order for covering this area? And at the end, I just select also an entrance point, and at the beginning, we will start by covering the headland bases. So in fact, we will start at that point here. We will just cover those headland bases, so we will clean them, and after that we will start working on the tracks. And as you can see here, because the 20 meters operating width of the vehicle, for example, so it's easy to finish one track and to enter to the next track directly, because 20 meters it's larger than the minimum turning radius of the vehicle. So turning time is just, I use this pi turning time, which is simplest. And after that, I can convert this one into XML file, and I can display it in Google Maps, so we can just have it and test that it's fine. And after that, of course, we need to test it with the robot. So at the end, it's this manual clearance of landmines is expensive and dangerous. because of lack of accurate records of the minefields. I mean, they don't have any record, in fact. And also, if they have records, it's not correct and it's not accurate because I mean, sand is keep moving all time. Increase the sensitivity of the mines, since they have been implanted for more than 60 years in World War II. So also locations and sensitivity, it's lots of uncertainty, in fact, about this. The shifting also of mines and the shifting of sands, which view the mines deeply and makes directions more difficult. So it's really hard problem to solve, and it's a very slow process, and the high cost associated with training and accommodations in remote areas, because those areas are in the desert. So in fact, it's very, very expensive to send people, and it costs a lot, lots of money. So using those autonomous systems or autonomous vehicles or robots for solving this problem, I guess it will be very important. It will speed up the process, and it will also reduce the risks, amount of risk, and the cost associated with this problem. Yes. And of course, if we can use, for example, I just suggested using interactive tool, such as Google Maps, for example, to just show people that we have those areas and how much cost, because people are not aware about this problem, in fact. So if we can use, maybe using robots or using Google Maps for presenting those landmines, landmine fields, and how expensive to solve those problems, maybe we can attract the attention of people to support those efforts. Yeah, thank you very much.
Especially the British and the Germans.